finish our discussion of Galois theory, we're going to look at a particular application, and that is the idea of solvability by radicals. The idea is that for certain types of polynomials, you can express all of their roots using algebraic expressions involving rational numbers and the field operations and extraction of roots. The quadratic formula is the most famous example of this, of course. However, there are also formulas for the roots of degree 3 and degree 4 polynomials over the rational numbers. However, as we will wind up proving, though it's going to take a little bit of work, there does not exist such a formula for the roots of degree 5 polynomials. And that's because there exist degree 5 polynomials that have roots which cannot be expressed using field operations, extraction of roots, and rational numbers. We'll be able to give a very, very simple example of such a polynomial, as well as an algorithm or a way of generating as many of these examples as you like. Now, in order to put our work on a proper theoretical context, we need the following definition, which encapsulates this idea of being able to express a root in terms of addition, subtraction, multiplication, division, and roots. So definition 180. Let's let f be a field, and let's let little f be a polynomial over the field f, and we say that f is solvable by radicals if there exists an extension field E of f such that f splits in E, and there exist a1 through an in E such that two things are true. First, that E is the smallest field containing f and a1 through an, and for each I from 1 to n, there exists a ki, a natural number that's greater than 0, such that ai to the ki belongs to the field that contains the smallest field containing f and a1 through ai minus 1. So the idea behind being solvable by radicals means that the polynomial splits in an extension field which can be obtained essentially by adjoining roots of elements of the field that you start with. So, for example, we can look at the polynomial f, which is x to the 4th plus 6x squared minus 4, which is contained in the polynomial ring over the rationals. This is solvable by radicals. Since we can use the quadratic formula to find that the roots of f are plus and minus the square root of -3 plus or minus the square root of 17. Now, these roots here don't immediately satisfy this condition required by the a1s through the ans. And so if we say that E is the field generated by the square root of -3 plus the square root of 17 and the square root of -3 minus the square root of 17, well, this is certainly the splitting field for for f, but it doesn't exactly show that this f is solvable by radicals by this definition. However, if we include an additional element of this field, which is the square root of 17, which certainly exists in the field E, then we could say that the field E is the smallest field containing the rationals. I should be using the rationals here instead of F. So the smallest field containing the rationals and the square root of -3 plus the square root of 17. Now, this element, if you raise it to the second power, belongs to the field Q with the square root of 17. And then we can throw in the other one as well. And the square of this element belongs to the field containing Q and the first two elements. So the idea behind being solvable by radicals is that if you keep throwing in roots of elements of the previous field, eventually you'll get to a field in which F splits. So it turns out that the Galois group of the splitting field of a polynomial that's solvable by radicals has a particular property. There's a group theoretic property of the Galois group of the field extension that tells us about the polynomial being solvable by radicals. So we're going to give the definition of this group property, a few examples, and then show the implication that we need. So definition 181, a group G is called solvable. This term comes back to exactly what we're going to be talking about, that the Galois group is going to be solvable exactly when polynomials are solvable by radicals. So a group G is solvable if there is a sequence of subgroups the trivial subgroup being called H0, and that's going to be a subgroup of H1, which is a subgroup of H2, etc., up through Hn, which is the whole group G, such that for each index I, we have that Hi minus 1 is a normal subgroup of Hi, and the quotient Hi mod Hi minus 1 is abelian. Essentially, what a solvable group has is enough normal subgroups. The normal subgroups inside a solvable group are dense enough that you can build a chain of them up to the whole group, such that every time you move from one normal subgroup to the next, their quotient is, or their factor group is abelian. And so this is what we call group G, and we're going to see that some groups are solvable and some groups are not. So for example, any abelian group is solvable. Any abelian group G is already solvable, since we can take the sequence of subgroups, the trivial subgroup, which is a normal subgroup of G itself. And since we have that G mod the trivial subgroup is isomorphic to just G as groups, and therefore, since G is abelian, this quotient factor group is abelian, and so the group G is solvable. For a less trivial example, we have that S3 is solvable. We looked at that last time as the Galois group of the splitting field of x cubed minus 2 over the rationals. So in order to prove this, we need to come up with a sequence of subgroups. So we're going to take the subgroup, the trivial subgroup, which we always have to start with, and then we're going to look at the subgroup generated by the 3-cycle 1, 2, 3, and that's going to be a subgroup of S3. So we can show that that all of these are normal containments. The trivial subgroup is always a normal subgroup of anything that that it's a subgroup of, and then it turns out that the subgroup generated by 1, 2, 3 is in fact a normal subgroup of S3. In fact, it's the alternating group of the alternating group on 3 elements, and it turns out the alternating group is always a normal subgroup of the symmetric group. And we have that the subgroup generated by the cycle 1, 2, 3 modulo the trivial subgroup 1 is isomorphic as groups to the trivial subgroup 1, or to the, not trivial, to the subgroup generated by 1, 2, and 3, and this has order 3, and hence is abelian. Remember that we've shown that any group of order 5 or less is abelian. The smallest non-abelian group has order 6. Also, we have that S3 mod the subgroup generated by 1, 2, and 3. The order of this group is going to be the order of S3 mod the order of the subgroup 1, 2, 3, which is 6 over 3, which is 2. And again, there's only actually one group of order 2, and it's abelian. So that means that S3 mod the group generated by the cycle 1, 2, 3 is abelian. So this shows that the symmetric group on 3 elements is solvable. However, the symmetric group on 5 elements is not solvable. So S5 is not solvable. And checking this requires a few things to check. So first of all, let's let H be a normal subgroup of S5, be a proper, non-trivial, normal subgroup of S5. So H doesn't just contain the identity permutation, but it's not all of S5, it's something in between. Now what we can show here is the following. Given any permutation sigma and any transposition AB, we have that the product AB sigma AB is the permutation that looks like sigma but switches the roles of A and B. Basically, what we think about when we think about what this permutation does, when we apply it to an element, the first thing is we apply the transposition AB. So that switches the roles of A and B, and then sigma does its thing, and then we switch back the roles of A and B. So this whole permutation is going to behave just like sigma on anything that's not A or B. And then when we apply it to A, we're going to switch the roles of A and B. It's going to do it's going to do something to B. It's going to do what sigma normally does to B, but then it's going to switch B back to A, and similarly in the other direction. So what this means is that since H is a normal subgroup of S5, if it includes any sigma, it has to include AB sigma AB for any A and B. So what that means is that if H contains any permutation, it includes all permutations of that disjoint cycle decomposition type. Because if it includes any permutation that can be written in the form of disjoint cycles, and then simply by repeatedly multiplying by these transpositions, we can exchange the roles of any of those pieces within the permutation, and so if H contains something of a particular decomposition form, it has to contain all the things of that form. So that means that we can look at what H can be. There's only so many things that H can be. So there are only 7 different disjoint cycle decomposition types in S5. So we have the following cycle decomposition types. We have just the trivial, the identity decomposition, the identity permutation. That's pretty trivial. Then we have all of the transpositions, AB. We have all of the 3 cycles, A, B, C. We have all the 4 cycles, A, B, C, D. We have all of the products of transpositions, disjoint transpositions, AB times CD. We have all of the 5 cycles, A, B, C, D, E. And then we have all of these cycles of the form ABC times DE. And we can actually count how many of these there are. So there is only one identity permutation. There are 10 transpositions. So that's 5 times 4 divided by 2, because there are 5 options for A, 4 entries for B, but then either A or B could start it, and it would be the same transposition. Similarly, for the 3 cycles, that's 5 times 4 times 3 divided by 3, because there are now 3 things that could start this cycle, which gives us 20. Of the 4 cycles, we've got 5 times 4 times 3 times 2, all divided by 4. So there are 34 cycles. For the product of two cycles, we can have 5 times 4 divided by 2 for the first transposition, and then 3 times 2 divided by 2 for the second transposition. But then we've got to multiply by 1/2, because ABCD is the same as CD times AB. So all that together gives us 10 times 3 times 1/2 is 15. There are 5 times 4 times 3 times 2 times 1 divided by 5, which is 24, 5 cycles. And then finally there are 5 times 4 times 3 divided by 3 times 2 times 1 divided by 2, which is 20 permutations of the form of a 3 cycle times a disjoint 2 cycle. And the point is that if F contains even a single member of one of these classes, it has to include all the members of that class. So we can eliminate some things right away. Let me number these as class 1, 2, 3, 4, 5, 6, and 7. So H does not include class 2, since then it would include all of S5. Because if H included all the transpositions, then it would have to include all of the permutations, because all of the permutations are products of transpositions. Let's see. If then if H contained class 7, then we could take any transposition A, B, C, D, E, and cube it. That would have to also be an element of H, but that would be DE. And DE does not belong to H, so H can't include class 7. That's a contradiction. We can similarly go through and say that it does not contain class 4. And this one's a little more complicated, but if H contained class 4, then it would have to contain 1, 2, 3, 4 times 1, 5, 3, 2, that times 1, 2, 4, 5, and this turns out to be the transposition 1, 2, which does not belong to H. So H does not include class 2, class 4, or class 7. So we want to look at, doesn't include classes 3, 5, and or 6. And here we can look at what we need in order to make sure that H must divide the order of S5, which is 120. So H certainly has to include the identity element, and then it might include something of size 20, might include something of size 15, and might include something of size 24. And it turns out that the only combinations of these numbers that will give you something that's that divides 120 is if you include all 4 of them, or if you include the first one and class 5 and 6. But so this shows that H must contain class 5 and 6. So we just making sure that it has to, the order of H must divide 120. But then it turns out that if you include class 5 and you include class 6, then there's a product of 2 transpositions with a 5 cycle that gives you a 3 cycle. So that means that H contains class 3. So we have that there is in fact only one non-trivial proper normal subgroup of H5. So H must be the union of classes 3, 5, 6, and 1, of course, i.e. H must be the alternating group of order 5. The alternating group of order 5 is the only proper non-trivial normal subgroup of S5. So that means that the only possible chain of subgroups that would possibly recognize the solvability of S5 would be the trivial subgroup, which is a normal subgroup of H, which is the alternating group on 5 elements, which certainly is a normal subgroup of S5. But we have that A5 modulo the trivial subgroup is isomorphic to A5, which is not abelian. So that tells us that S5 is not a solvable group. So some groups are solvable, some groups are not solvable. It turns out that the symmetric group of order the symmetric group on 1 elements, 2 elements, 3 elements, and 4 elements are all solvable, but the symmetric group on 5 or more elements is not solvable. Essentially, what's happening is that the symmetric groups, it's really hard to be a normal subgroup of a symmetric group. And so once the symmetric group gets large enough, there are only so many normal subgroups inside of it, and there aren't enough of them to build this stack where they're all close enough together that their factor groups are abelian. Okay, so it's going to turn out that when you've got a polynomial that's solvable by radicals, then it splits in a field where the Galois group of that field is solvable. Now, this is a big result, very important, but to prove it, we do need a couple of preliminary results. So let's start with Theorem 182. So let's let F be a field, n a positive natural number, such that the characteristic of F does not divide n. So if the characteristic of F is 0, this applies to any n, and if the characteristic of F is a prime number p, you just need n to not be divisible by p. If this is the case, then there exists a field extension E of F containing a primitive root of unity, a primitive nth root of unity. That is an element omega such that omega to the n is equal to 1, but omega to the j is not equal to 1 for any j's that are less than n. It turns out that finding primitive roots of unity is going to be very important to what we do next. And so knowing that they exist is going to be important. The proof goes as follows. Let's let F be x to the n minus 1 inside f of x. And we're going to basically show that the splitting field for f contains a primitive root of unity. Let E containing f be the splitting field for little f. Now, we have that f prime is equal to nx to the n minus 1. And here's where we're using the fact that the characteristic of f does not divide n, because this means that f prime is not equal to 0, and we have that 1 is equal to 1 over n times x times f prime minus f. So we multiply f prime by x, we divide by n, and we get x to the n. So x to the n minus x to the n minus 1 equals 1. And this belongs to the ideal generated by f and f prime. So this means that f and f prime equal all of the polynomial ring f adjoin x. And so remember that this shows that f has no repeated roots in E. So the ideal generated by a polynomial and its derivative being the whole polynomial ring shows that f has no repeated roots in any extension field. So that means that in E, where the polynomial f splits, that means that there exist n distinct roots, alpha 1, alpha 2, up through alpha n, for f in E. Further, we have that this set forms a multiplicative group. Because if we take any alpha I times alpha j and we raise it to the nth power, that's alpha I times alpha j, alpha I to the n times alpha j to the n, which is 1 times 1, which is 1. So that means that alpha I times alpha j equals alpha k for some k. So that means that the alpha 1, alpha 2, up through alpha n form a group. All right, so we have that this set of n distinct roots forms a group. What we want to show is that this group is actually this group is actually cyclic, which will prove that that any generator of this group is a primitive nth root of unity. So we have that. We have that this set A, or this group A, which we're by which we're denoting the set of elements alpha 1 through alpha n, is equal to the direct product of GP1, GP2, up through GPN, where, or GPM, I should say, not the same number, where each GP1 is the subgroup of A containing the elements whose order is a power of the prime number pi. The pi are distinct, and we have that n is equal to the pi are distinct, and it turns out that n is a product of powers of the pi's. So this comes from the proof of the fundamental theorem of finite abelian groups. A is certainly a finite abelian group, and so a lot of the work that we did in understanding that structure comes there. Now, this statement right here actually comes from part way through the proof, where we can take any finite abelian group and write it as a direct product of groups of prime power order. So for each I, let's let xi be an element of GPI of maximal order. Now, each xi has to have an order which is a power of pi. So I should say this is isomorphic. Let's say that this maximal order is a pi to the li. It has to be some power of pi. Actually, let me be consistent with the notes and say pi to the di. So now, let's take the element x, which is the element x1, x2, up through xm. Now you'll remember that the order of an element of the direct product is the least common multiple of the orders of each of the components. But each of these components has order, which is a power of a prime number, and they're all different prime numbers. And so this element has order, which is just equal to the product of all of those. The least common multiple of things without any common factors is just the product of all of them. So it has order P1 times L1, or P1 to the L1, P2 to the L2, up through PM to the LM. Sorry, D1, D2. I'm writing down L's where I mean D's. And I want to call this L. Now, also, if y, which is y1 through ym, is any element of this direct product GP1 up through GPM, then y to the L is equal to then y to the L is equal to the identity. Because if y to the L will mean taking each of these y elements and raising it to this power, which is a product of a whole bunch of primes, and because we chose the xi's to have maximal possible order, then the y's have to have order that are less than or equal to this. So the order of y1 is less than or equal to the order of x1, and we're raising it to a multiple of the order of x1, so we're going to have to get the identity. Okay, so each of these y's corresponds to an element of A over here. So this means that any element alpha I has order at most L in the group A. So for any I, we have that alpha I to the L is equal to the identity element of A, which is actually just equal to 1. 1 is certainly a root of F, and it's also going to be the identity element of this subgroup of E. So each alpha I is a root of the polynomial x to the L minus 1. So that means that x to the L minus 1 has at least n different roots. So that means that L is greater than or equal to n, which is the order of A, which is the order of this group, which I'll call G for the sake of ease of notation. But the order of G is at most the orders of each, the products of the orders of each of the, or rather, at least the products of the orders of each of the groups. Sorry, it's equal to that, and each of the orders of the groups GPI is greater than or equal to Pi to the Li. So this is greater than or equal to P1 to the L1, which is the order of X1, times P2 to the D2. Up through PM to the DM, which is L. So we have equality throughout. So that means that there exists an element x. This element x has order L, and L is equal to the order of A. So that means that actually G is a cyclic group. So A is a cyclic group, and so that means that there exists a primitive, or so I should say, any generator of it as a group is a primitive nth root of unity. Now, this proof does not show that there necessarily exist primitive roots of unity for any n that is divisible by the characteristic, but that situation doesn't come up terribly often. We're not going to need it so much here. We're mostly going to be dealing with fields of characteristic 0. Okay, so we can construct fields with primitive nth roots of unity for any n not divisible by the characteristic. We need one more theorem, the proof of which is going to be an exercise. Theorem 183. Let's let G be a group, and let's let H be a normal subgroup of G. Part 1. If G is solvable, then G mod H is solvable. This is going to be very important to us. We're going to use this a few times in the proof coming up. We're going to want to prove that groups are solvable, and if you can express that group as a factor group of a solvable group, then you're just done. Number 2, if H is solvable and G mod H is solvable, then G is solvable. So this is saying basically that if the two pieces that go into making up G are solvable, then G itself is solvable. The proof is an exercise, but to give a hint as to how you start, for part 1, we know that if G is solvable, then we can construct this sequence of normal subgroups H0 to H1 up through Hn, which is G, and we want to construct a similar sort of thing down here to G mod H. Well, we know that there exists this homomorphism, the projection homomorphism, which takes any element of G and takes it to the coset with that representative. And you can try applying that same homomorphism to each of the H's that you had before, and you're going to get a sequence of subgroups of the group G mod H. Now from there you have to prove that each of those groups is a normal subgroup of the next one above it, and that when you take the quotient of two of them you get an abelian group. You can, I recommend taking a look back at the theorems that we proved in the sections on groups about what happens with homomorphisms of groups, and what happens when you have a surjective homomorphism of groups like we do here. This pi homomorphism is surjective. Now for part 2, if H is solvable and G mod H is solvable, you want to kind of do similar sort of thing. So you're going to want to build up a chain of subgroups of G in 2 parts. So the first part is that we know that we've got a chain of subgroups that has the properties that we want, that goes up to H, but then we need to get from H up to G. What we know, though, is that if we look down at the level of G mod H, by applying this same homomorphism pi, then we know that there exists some subgroups of the factor group G mod H that have the properties that we want, that they're normal, and that their quotients are abelian, and you want to look at what happens when you pull those back, when you look at the preimage of the function of the subgroups K when you pull them back along this function pi. So the idea is that you'll be able to construct a chain of subgroups this way as well and prove that they have the properties that we want. All right, so now we're ready to get to Theorem 184. Now there are a lot of moving pieces on this one. I'll try to make it as clear as I can, but we're going to be making reference back to both of the theorems that we just proved, as well as some other properties of field extensions that we've been talking about for a while. So let's let F be a field of characteristic 0. We're not going to try to prove it in more general cases yet. Of characteristic 0, and let's let little f be a polynomial inside the polynomial ring over the field f. And let's suppose that we have this a polynomial which is solvable by radicals. Let's let f of a1 through an basically be a realization of that solvability, be an extension field such that, or in which little f splits, and such that for each I, there exists a ki positive, in fact it's going to be greater than 1, such that ai to the ki belongs to the field f of a1 up through ai minus 1. I'm going to call this the whole big field at the top E. And the conclusion of all this is that the Galwa group Galwa E over F is solvable. Sorry, I made a slight technical difference here, but it's actually going to be important for us. This E might not be the full thing here, might not be the full field here. We know that little f splits in this big field f of a1 through an. So let's let E be the splitting field for f. Let E be the splitting field for f in this bigger field f of a1 through an. And then the conclusion is that the Galwa group of E over F is solvable. In theory, this larger field, F of A1 through AN, might be larger than E. In practice, the splitting field E can be written in this way. Okay, so this will show, once we've proven it, that if we take a polynomial which is solvable by radicals, then and take its splitting field, then the Galois group of that splitting field will be solvable. The way that that's going to show us that certain polynomials are not solvable by radicals is by showing that some polynomials have non-solvable Galois groups when you look at their splitting field extension. So let's get started on this. We proceed by induction on n. Now, typically, most commonly when we do induction, the base case is pretty easy, and it's the inductive step that requires a lot of work. This proof is very much the opposite. The base case here showing that this step goes up when you're just taking a single a1 over f is going to be where most of the work shows up. About 75-80% of the work is the base case. The inductive step is a fairly immediate consequence of that. So let's get started and suppose that n is equal to 1. Let's let k be k1 just for the sake of convenience. And let's let a be this a1 to the k, which lies in f. So by hypothesis, we have that a1 to the k1 lies in f. Now we have that f is a subset of E, which is a subset of f of a1. So we have that the polynomial f splits in f of a1. Its splitting field could, in theory, be smaller, and that's what we call E. Now, by theorem 182, we can let omega be a primitive kth root of unity in an extension field of f of a1. So now note that in the field f of a1 comma omega, we have that a1 omega, a1 omega squared, etc., up through a1 omega to the k minus 1 are k distinct roots of the polynomial x to the k minus a. And this is because we know that a1 to the kth is equal to a, and omega to the kth, or omega squared to the kth, or omega to anything to the kth is going to just be 1. And let me call this polynomial g, and this polynomial belongs to the polynomial ring over the field f. And so thus we have that f of a1 omega is a splitting field, or is a field, rather, in which G splits. Now, we're going to claim that the Galois group of f of omega over f is abelian. We claim that the Galois group of f of omega over f is abelian. So to see this, note that 1 omega squared up through omega k minus 1 is a basis for f of omega as an F vector space. And sorry, we don't want K here. We want M here, where m is the degree of the minimal polynomial for omega over f, which might be less than k. So this means that an element phi inside the Galois group of f of omega over f is determined entirely by where it sends omega, i.e. by phi of omega. But we have that omega is a root of x to the k minus 1, so phi of omega must be equal to omega to the I for some I, because these are what these are all the roots of x to the k minus 1. Now, similarly, we can let psi be another element of the Galois group of f of omega over f, with psi of omega equaling omega to the j. Now we have the following. If we have phi of psi, this element of the Galois group is also going to be determined entirely by where it sends omega. Now, psi of omega is omega to the j. Phi of omega to the j is phi of j raised to the I, which is, or omega to the j raised to the I, which is omega to the j times I, or equivalently I times j, which is omega to the I to the j, which is psi of omega to the I which is psi of phi of omega. So this means that phi composed with psi is the same as psi composed with phi, and so that means that the Galois group of f of omega over f is abelian. So now we're going to show that another Galois group is abelian. We're going to show that the Galois group of f of a1 and omega over f of omega is abelian. So now we claim that the Galois group of f of a1 omega over f of omega is abelian. This is going to go similarly to the previous one. So we have that phi in this Galois group, f of a1 omega over f of omega, is determined by where it sends where it sends a1. So we have that as we mentioned before, that the a1 times omega to the various powers are distinct roots of g. So since a1 is a root of g, which remember was the polynomial x to the k minus a, we must have that phi of a1 is equal to a times omega to the I for some I, because phi must take a root of g to another root of g, and all the roots of g look like this. So similarly, let's let psi be another element of this Galois group, a1 omega over f of omega, sending phi of a, or psi of a1 to a omega to the j. So now, again, we can look at their composition. If we look at phi of psi of a1, that's phi of a omega to the j, phi of a1 omega to the j. Now, phi sends a1 to a1 omega to the I, but now that phi is an element of the Galois group of f of a1 and omega over f of omega, we have that phi fixes omega. So we just get a1 times omega to the I times omega to the j, which is a1 times omega to the I plus j, which is a1 times omega to the j plus I, and we can unwind it in the other order. So this is equal to psi of a1 times omega to the I, which is also psi of phi of a1. So this means that phi composed with psi is equal to psi composed with phi, and so we have that the Galois group of f of a1 omega over f of omega is abelian. So now that we have some groups, some Galois groups that we know are abelian, we're going to use the fundamental theorem of Galwa theory in order to construct a sequence of subgroups that shows solvability of a Galwa group. So we have that if we look at the identity automorphism on f of ai a1 omega, this is a normal subgroup of the Galwa group of f of a1 omega over f of omega, which is a normal subgroup of the Galwa group of f of a1 omega over f. And we know that we have this normal relationship here because f of omega is the splitting field of a polynomial over f, namely the x to the k minus 1. So by theorem 180, that is the fundamental theorem of Galois theory, we have that the Galois group of f of a1 omega over f mod the Galwa group of f of a1 omega over f omega is isomorphic as groups to the Galwa group of f of omega over f. And we know, or we've proven, that the Galwa group of f of omega over f is abelian. So we showed that this middle subgroup is abelian, and then we've shown that the quotient of these two is abelian by using the fundamental theorem of Galois theory to show that it's the Galwa group of some other field extension, and by proving that that field extension, the Galwa group of that field extension, is abelian. Thus, we have that the Galwa group of f of a1 omega over f is solvable. Now, this isn't quite what we wanted. We wanted the Galwa group of f of a1 over f to be solvable. But we can get that again by the fundamental theorem of Galwa theory. So we have that the Galwa group of f of a1 over f is isomorphic to the Galwa group of f of a1 omega over f over the Galwa group of f of a1 omega over f of a1. And we don't know about the Galwa group of f of a1 omega over f of a1, but we don't need to. What we know is that this this top group is solvable. And so we have that the Galois group f of a1 over f is the factor group of a solvable group, and hence is solvable. So hence the Galois group of f of a1 over f is solvable by Theorem 184. Okay, so that handles the base case. But as I said, the base case is definitely the hardest one here. So we've shown that if a field splits inside, or if a polynomial splits in, is solvable by radicals and splits inside the field that you get by joining a single element, which is the root of some element of the original field, then the Galois group of the splitting field of that polynomial is solvable. Oh, sorry. So one more step, going through almost exactly the same thing again. We have that the splitting field, the actual splitting field, yes, sits between f and f of a1. So we have that the Galois group of E over F is isomorphic as groups to the Galois group of F of A1 over F mod the Galois group of F of A1 over E. And once again, we know that the top group here is solvable. So the Galois group of E over F is solvable. Definitely don't want to miss out on that last step. Again by Theorem 184. So this handles the base case where you just need to adjoin a single root, but what about when you have to adjoin several roots to get some of the nested square roots or cube roots expressions that we sometimes get? All right, so now for induction, suppose that n is greater than or equal to 2 and that the result holds for n minus 1. So now let's let k be f of a1. We have that E is the splitting field for little f in k of a2 up through an, and for each I, there exists a ki greater than 1 such that ai is in ai to the ki is in k of a2 up through ai minus 1. Oh, okay, so technically we need to be a little more careful here. Let's say that we let E prime be the splitting field for f inside this thing over k in order to over the field k. So the difference here is that the actual splitting field E might not include A1. Because there might be a difference between f of a1 through an and E itself. E might not actually include a1, so we need to be a little bit careful here. So this E prime might be slightly bigger than E, but we're going to be able to correct for that. So let's let E prime be the splitting field for F over this field K, F of A1. We have this same property that we need. And so by the inductive hypothesis, we have that the Galois group of E prime over K is solvable. And then by theorem 180, we have that the Galois group of K over F is isomorphic to the Galois group of E prime over F mod the Galois group of E prime over K. Now, since we have that the Galois group of E prime over K is solvable by the hypothesis, it suffices to show that the Galois group of K over F is solvable. Because if we can show that this normal subgroup of the Galois group of E prime over F is solvable, and that the factor group is solvable, then that means that the original group, the top group in the factor group, is solvable. But K is just F over A1. This is just the base case again. So this is just the base case. So we've already proved that F of A1, the Galois group of F of A1 over F is going to be solvable. In fact, it's only part of the base case that we looked at. So by theorem 184, we have that the Galois group of E prime over F is solvable. So then to get back down to E, we have that F is contained in E is contained in E prime. E prime can only be a little bit bigger than E. So that means that the Galois group of E over F is isomorphic to the Galois group of E prime over F modulo the Galois group of E prime over E. And so this is solvable. Again, by theorem 184. So this proves the result that if I have a polynomial whose roots are, which is solvable by radicals, basically whose roots are expressible as algebraic expressions involving elements of the base field, addition, subtraction, multiplication, division, and roots, then the Galois group of the splitting field of that polynomial will be solvable. So we can use this to show that a quintic formula, a formula in square roots for the roots of a degree 5 polynomial, cannot exist. So let's see how that goes. So this is often called the insolvability of the quintic. Let's let f be a polynomial with rational coefficients, be an irreducible polynomial of degree 5. So that means that f has 5 roots, alpha 1 through alpha 5, inside the rational numbers. So that means that if E is the splitting field for F, then then we have that E is equal to F of alpha 1 up through alpha 5. Also, we have that any element phi inside the Galois group of E over Q, oh, I don't need F here, I just need Q. Any element phi in the Galois group of E over Q permutes the alpha i's. Because it has to send any root of f to another root of f. So this means that the Galois group of E over Q is a subset, or is isomorphic to, I should say, a subgroup of S5, the set of permutations on 5 elements. So we want to identify what kind of subgroup of S5 is this Galois group, and there can be some differences. Since F is irreducible, we've assumed F is irreducible, so given that we have that the index of any Q of AI over Q, or rather the order of this extension, is equal to 5 for any alpha I, we have that the Galois group of Q alpha I over Q has order 5, and so 5 divides the order of the Galois group of E over Q, because this group is a subgroup. Or sorry, not because this is a subgroup, but because we have that that the order of E over Q is equal to the order of E over Q of alpha I times the order of Q alpha I over Q, and this is equal to 5, and this is equal to the order of the Galwa group of E over Q. Now, one thing that this means is that the Galwa group of E over Q must include an element of order 5. So that means that the Galwa group of E over Q contains an element of order 5. But the only elements of order 5 inside the symmetric group on 5 elements are the 5 cycles. So this tells us that there exists some automorphism of the splitting field of F which cycles the roots of F around and has order 5. We can go further. If one of these AIs is not real, then the conjugacy, the conjugate automorphism, phi from C to C, which takes an A plus BI and sends it to an A minus BI, fixes the coefficients of F, and so sends alpha I to another alpha I, to another alpha J, I should say. But we also have that phi has order 2 in the Galois group of E over Q. So this means that there exists elements of order 2 in the Galois group if f has at least one non-real root. So if f has exactly 2 non-real roots, then this phi here corresponds to a transposition. That is a 2 cycle in S5. So if we're looking at an irreducible polynomial of degree 5, which has, over the rational numbers, which has exactly 2 complex roots, or non-real roots, I should say, then the Galois group of the splitting field of that polynomial is isomorphic to a subgroup of the symmetric group on 5 elements that contains a 5 cycle and a 2 cycle. It's an exercise to show that the only subgroup of S5 containing a 5 cycle and a 2 cycle is S5 itself. So that tells us that if we're in this situation, then where we've got an irreducible polynomial with exactly 2 non-real roots of degree 5, then its Galois group is isomorphic to S5. So in summary, if f inside Q adjoin X is irreducible of degree 5 with having exactly 2 non-real roots, then the Galois group of the splitting field of E over Q is equal to S5, which is not solvable. Thus, f is not solvable by radicals. Meaning that at least one of the roots of f cannot be expressed using just addition, subtraction, multiplication, division, and roots of rational numbers. Now, it's actually not too hard to come up with polynomials that have this property. Eisenstein's criterion is a really good way of coming up with irreducible polynomials. And then you can go from there to make sure that they have exactly 2 complex roots. The easiest way to do that, of course, is to show that they have exactly 3 real roots, because an irreducible polynomial of degree 5 must have a total of 5 complex roots. If 3 of them are real, then 2 of them have to be complex, and we get this result here. So the simplest example that I can find, I think one would have to work really hard to find a simpler example of a polynomial that's not solvable by radicals over the rationals, is x to the 5th minus 4x plus 2. Just 3 terms, really simple. This is irreducible by Eisenstein's criterion. Because all of the coefficients after the first are divisible by 2, and the constant term is not divisible by 2 squared. So we can note that if we were to graph this polynomial on a Cartesian plane, then notice that f of 0 is 2, but f of 1 is equal to -1. And we know the end behavior, of course. So that means that the graph of this polynomial must look something like this. So it has at least three roots, three real roots. If we look at the derivative of f, we get 5x to the fourth minus 4, and we can see that this polynomial, 5x to the fourth minus 4, has only two zeros, has only two real zeros, and as a result, this the original graph has only two turning points. So there's no possible way for this function to have more turning points than we've sketched out, which means that it can't have more than three real roots, which means two of its roots must be complex. Exactly two of its roots must be complex, which means that its roots, at least one of its roots, cannot be expressed using radicals.